Just an announcement to begin with. I had listed the first exam as being on October 9th, and I'm tentatively thinking of moving it back to October 21st, which is after fall break. And the reason I'm thinking about moving it back by a week and a half is so that I can test you over all the database material, and then you don't have to worry about being tested over it for the final. If I hold the exam on October 9th, then I can't test you over either normalization or physical database design, and it will be another like 8 weeks before you would be able to be tested over the database materials. So I haven't made a firm decision about that, but at this point I'm about 75% confident that I'm going to change the exam date to be October 21st, which would be after fall break. And that would mean we would start with, everything else would move up by a day, so the Pearl lectures would start on Thursday, October 9th, rather than on Thursday, October 14th. So I know also that several of you were going to the Grace Hopper conference on, I think, that week too, so that may solve some problems that was being faced there as well. I'll make a final announcement about that next week. Second thing, had a question about how you express subqueries in the tuple relational algebra. So it may not be readable. Let me go to the Piazza question. Okay, so here was the question. Can you read that in the back? Yes or no? Okay, so the question is, this is getting, basically just selecting rooms that are at the, this actually is not, sorry, I actually had not read the question carefully enough. I'm going to change this slightly. So I am going to assume it is where room.hotel number equals hotel.hotel number and hotel.name equals Marriott. This is still a subquery. Okay, so the question is, how do you express that in the tuple relational calculus? The answer is you use an existential quantifier. So remember, the only free variables are those that appear in the, whose attributes appear in the select list. So only room's attributes appear in the select list. Therefore, it can be the only free variable. So I'm going to write r dot room number. And it can be a free one. So we're going to have r ranging over the room relation. Then you're going to use an existential quantifier for hotel. So basically the query is to list all rooms that are in the Marriott. Okay, so, and there exists H such that H is in hotel and H dot name equals Marriott and H dot hotel number equals R dot hotel number. Okay, so that's how you represent that particular subquery. It's with an existential quantifier because the subquery, by definition, is binding some tuple variable. So use an existential quantifier when you're writing your subqueries. Does that make sense? And it's a lot easier to post it here because, quite frankly, it's a little more difficult to get those symbols into Piazza. Have to figure out how to do that. But this is a quick way. Okay, so questions? We good? Okay. So last time we finished up, we were talking about the multiplicity of relationships. So we're going to finish that today, talk about a couple common mistakes that are made in ER diagrams, and then we're going to go over a case study that I posted. The reason we're going over this case study is the first time I taught the course, I gave something like this as a homework assignment and then separately as an exam problem, and the results were hellacious. So I've learned that I need to go over a case study in class. So I understand some of you might get a little bit bored. Just be aware if you tune out, you're probably going to bomb the homework assignment and the exam problem completely, and it'll be worth close to a letter grade. Okay, you can see from the thing I posted was worth 28 points on an exam. And the first time I taught the course, I think the average was somewhere between 5 and 10 points on the question. So it's clear that I can go over the concepts, but unless I go over a concrete example, it doesn't really seem to sink in. Okay, so at the end of last time was saying that it's very frequent with a many relationship like this. So I'm having newspapers advertise as property for rent. And it's a many-to-many relationship because a newspaper may advertise one-to-many properties, and a property may be in zero-to-many newspapers. If it's already rented out and under contract, there's no reason to advertise it, hence the zero. Remember, the first number, the zero, represents the minimum participation rate, and the right-hand number represents the maximum participation rate, or the cardinality. So this is also the right way to write a many-to-many relationship. It makes it clear that it is a many-to-many relationship. Now, it's almost certainly going to get implemented as a relation when you map it to the relational database model. But in the ER diagram, it really needs to be shown as a many-to-many relation. The wrong way to show this many-to-many relation is a way many of you will be tempted to show it, which is like this. So you'll show it as two binary relationships, one between newspaper and advertisement, and one between property for rent and advertisement. And you see both arrows are going into the advertisement because you have newspaper lists in advertisement, and a newspaper can list one-to-many advertisements, and an advertisement appears in one and only one newspaper. And you may wonder, why is that? Well, think about it. An advertisement is going to presumably have a newspaper ID where it appears in, and a property ID that it is advertising. So it has exactly one newspaper ID and one property. So there's one tuple for each of those, hence 1-to-1. Same thing for property for rent. A property for rent can appear in multiple advertisements because it can appear in multiple newspapers. So you might have property for rent has a binary relationship with advertisement. But as I said, this is the wrong way to express the relationship because it completely obscures the fact that newspapers advertise properties for rent. Instead, you're creating this artificial entity called advertisement, sticking it into your entity relationship diagram and making it look like property for rent and newspaper have no relationship with each other. Instead, they have this relationship with advertisement, when instead the relationship is between the newspaper and a property for rent. So don't get, when you see something like this, where you have this kind of when you have two what I call one-to-many relationships coming into the same entity, make sure that you haven't accidentally used two binary relationships to represent a many-to-many relationship. Now, maybe it's legitimate, and they're two very different things, but in this case, it's not so. It is two very different kinds of things, and both arrows are going into the same box. If the arrows were going the other way, one arrow was coming in and one arrow was going out, that also would not suggest a many-to-many relationship. But the fact that both arrows are coming into the box and that they're one-to-many should at least raise a red flag that potentially there's a many-to-many relationship. The nail in the coffin that says yes, it really is a many-many relationship is when you consider what exactly would be represented in an advertisement, what information, and you realize, well, an advertisement would contain both a newspaper ID and a property for rent ID. That should be a tip-off, a huge tip-off now that there really is the relationship here is between newspaper ID and property for rent, not between a newspaper and advertisement and a property for rent in an advertisement. So the fact that when you consider what this entity would so-called contain and you find out that it has two foreign keys like that, that's a huge clue that you missed the relationship. Does that make sense? Okay. We talked about this last time, so I'm not going to go through it. We did not talk about this, which is how you determine the multiplicity of n-degree relationships where n is greater than 2. So ternary, quaternary. The way you determine it, so here's an example, is you fix two of the entities. So you pretend you have a occurrence or an instance of each of the remaining entities, and then you try to determine, based on that, how many instances of the remaining entity you can have. So we start by trying to figure out what this number here should be. Okay? So think of it as though you have a function where you have a staff person and you have a client. Okay? And how many branches can you have for a staff person who's registered a client? Okay, it's exactly 1. You can only have a client is going to be associated with a specific staff member and a specific branch. So it's both minimum of 1, which is the one here, and a maximum of 1, which is the one there. Okay, so we now go, we got that one. Now let's figure out if we have a staff person and a branch. What does that mean for a client? So we have a function with a specific staff person and a specific branch. So for example, staff member SG03 at branch B01, how many, it's not really a function, but I'm showing it that way, how many potential tuples or instances of a client might be associated with that staff person in that branch? Well, the answer is 0 to many. The staff person may have registered no clients, or the staff person may have registered an arbitrary number of clients. So the answer to that question is 0 to many. Okay, so the final one is how do we calculate the 1, 1 there. Okay, so we want to calculate this one, which means that we consider a branch and a client. So given a specific branch, let's say B003, and a client, say CL01, how many staff can have registered that client? The answer is exactly 1. We have to have at least one staff member register them, and at most one staff member can register them. So that's how we come up with those participation rates when we have a relationship whose degree is greater than 2. We consider all the remaining entities, substitute in a specific instance for each of those entities, and then decide how many occurrences of the remaining entity there could be, which is what this slide here says. You fix the n-1 values and then figure out how many occurrences of the remaining entity can occur. Okay, so that's why I said it can help to write it. I said F. It's probably better to just say it's a relationship D, because a function, no, a function actually can have multiple values for the same thing, so I shouldn't say that. So at any rate, I represented the relationship here as D, so if I had an instance of both A and B, and it turned out I could have either 0 occurrences of C or maximally 1, then you write 0 to 1 next to C. So questions about determining participation rates for ternary and quaternary relationships, or anything above 2? Yes? Just a sec. So what you want, you're asking about 0. Okay, so you're asking about this. You're saying how can this yield a 0 to many? Okay, so if you think about the relationship, so you have one staff member, we'll call it S03, and one branch, say 005. You think about how many clients could that person have signed up? Okay, worst case 0, the person is a horrible salesperson, doesn't get out there and sign up clients. On the other hand, they could be a real go-getter, in which case the sky's the limit to how many people they might have signed up. So that's why it's shown as 0 to many, because... Pardon? No, client is a strong entity. Client's a physical person. So remember I said strong entities, for sure, anything that has a physical presence is going to be a strong entity. Okay. Now, it may well be that if we have to express this register's relationship as a relation, then the register is going to be a weak entity, okay, because it doesn't really exist in the real world. So that would be a weak entity. But the 3, branch, client, and staff, they're strong entities. Other questions? Okay. So I'm going to skip over that slide. So there's 2 common problems that you can create with a entity relationship model, and they're called connection traps. And they often result in either a misinterpretation or a misrepresentation of certain relationships. And the 2 main types are so-called fan traps and chasm traps. Okay, and actually I will come back to the slide and I'll first illustrate it. So fan traps occur when you, okay. So there is a relationship here between staff and branch, okay? There is one. There's staff belong to branch. But the way that we've drawn this diagram, the diagram also suggests there's a relationship, because when you have arrow or lines, I should say lines, between entities, there's often a good chance that there's a transitive relationship. That is, if A has a relationship with B, and B has relationship with C, then there's a good chance that A has a relationship with C. It's not guaranteed, but there's a good chance that A has a relationship with C, so it's transitive, often transitive. But the way this diagram is written, notice the arrows. One arrow goes this way and the other arrow goes that way. Okay, so they fan out in opposite directions. Okay, so you have fanning out in opposite directions, which means, if you think about it in some sense, staff and branch are getting repelled like a magnet, pushing two things apart. It's kind of the antithesis of a relationship. It's kind of pushing apart. And if you go further and look at things, you can see what's going to happen. So we have a division D1, which is operating two branches, B3 and B7. And you have a staff member who belongs to division D1. But you have no way of knowing which branch staff member 37 belongs to, because divisions become a choke point. And the information has basically, at that point, been thrown away. You don't know which branch SG37 belongs to. You can typically fix this type of problem. So this type of problem typically occurs when you have two one-to-many relationships going in opposite directions. So here you have a one-to-many, here you have a one-to-many, and they're going in opposite directions. Typically, you can fix that by simply reversing the direction of one of the, or both of the arrows. So in this case, what we did is we still have division operates branch. That's the same that we had here. Division operates branch, except now it's right here. But we turned around. We no longer show a relationship from division to staff. Instead, we now show a relationship from branch to staff. So we reordered the relationships. That's more natural, right? Division has branch, branch has staff. So we resolved the fan trap. Okay, if you look at a diagram, you can see that it's now clear that SG37 belongs to branch 3. And you can further, through a join, deduce that that staff member belongs to division 1. So you haven't lost any information. See, back here, I also could find out that staff member 37 belonged to division 1, but I had no idea what branch that staff member belonged to. Now, there's a clear path that allows me to identify both the branch and the division. So when you look for these kind of traps when you finish the diagram, and you want to see whether there's certain information that you expect to be able to retrieve from the database that maybe you can't based on the way you drew the diagrams. And like I said, there is certain red flags that you should look for. In this case, the red flag you want to look for is the fact that you have two one-to-many relationships emanating in opposite directions. Again, doesn't guarantee it's a fan trap, but it's something that bears looking into. Okay. Second problem is a chasm trap. That's where it looks like you have a relationship. So here the arrows go in the same direction, right? They're both going in the correct direction. So it looks like a branch may in fact have some relationship with property for rent. But the path, notice there's a 0 to 1 sitting right there, meaning that a property may not be overseen by any staff member. What that means in practice is that that relationship may actually look like this. Branch goes to staff for a particular property, but there is nothing over there for property for rent. So because of this 0 to 1, that path may not actually exist the way you think it does. Okay? So here's an example. We have property PA14, and presumably it's associated with a branch. This diagram certainly allows the reader to assume that, and probably you do think that a property is associated with a branch. Now, a staff member may temporarily not be handling that property. Maybe the staff member just left the company, but the property is still attached to a branch. So you have a problem here. The staff member left, but now the property has been orphaned. That's a chasm trap. You can't determine which branch contains or manages property PA14. So the way you can fix that is two ways. First of all, you can create another relationship. So you can say branch offers property for rent. So now you have a relationship where a branch can offer one-to-many properties. A property is offered by one and at most one branch. So that resolves the chasm trap, because if you now look at it, there is a way around, even though there's no path from PA14 through here, I can get to a branch that way. So you do have a path. Now, the book conveniently dropped it and said, okay, was happy. It said, problem averted. No longer do we have a chasm trap. The book did not talk about the problem with this solution. There's a problem with this solution. Can anyone suggest what problem has been introduced by adding this relationship? Now, it makes it explicit in the entity relationship diagram that there is a relationship that always exists between a branch and a property for rent, and that is good. So in the diagram itself, it is fine to fix the trap this way. But there's an issue. If you go to implement this in a database, what do you think the property for rent relationship, what keys are going to have to be in it? What foreign keys? Hey, pardon? Branch number is one. Property, well, that's not a foreign key. Property number is the primary key. There's another foreign key. Pardon? Not client. Staff number. Okay? So you might have branch B003, staff 07. What problem might arise now? What problem might arise if a staff member moves to a new branch, like branch B005? Pardon? The model would be wrong because it still shows that the staff belongs to the BJ. Very good. There's a possible update inconsistency now because in staff, there's also staff number and branch number. And now you have redundant data. So to fix the chasm trap, we did it by introducing redundant data into our database. And if the staff member moves, say, to branch B05, I might forget to update it in property for rent. I have to remember now to update it in both places. And remember, that was the whole point of the relational model, was to remove this kind of redundancy because it could cause inconsistency. So the book did not address this issue, that in fixing a chasm trap, you could be introducing inconsistency problems into your database. So there's a trade-off here. Okay? Now, there might be ways to fix this problem without having to put another relationship like offers into the pudding, so to speak. Another way, can anyone think of another way that might be logical and might ensure that no staff member is ever without a staff, no property for rent is ever without a staff member overseeing it? No, you're in the same issue of you're introducing another relationship. I want to get rid of, what I want to do, I don't want to put this relationship in here. I would like to guarantee that I just have these two binary relationships. There's another way to fix this chasm trap. Pardon? It can't be null. You could force this to have a minimum participation rate of 1. For example, you might designate the manager of the branch to automatically get any property when a staff member leaves. So until the property is reassigned, you might be able to say that it's assigned to a manager. Or it might go to a default staff member. Okay? You can't do this unilaterally. You'd have to ask, is this an appropriate solution? Could we handle it that way by having any unassigned property for rent by default be managed by the branch manager? Okay? That fixes the problem. Now that 0 is replaced with a 1. There's no chasm trap anymore. So my point is, the book didn't explore every possible way to resolve a chasm trap. They showed you one way which introduces an inconsistency problem into your database. Okay, this is another way. Well, no, this is it's unnecessary because this is at the very end. So it's really okay for a staff member to not manage any properties. Okay, that doesn't lose any information. If you go, they call this a semantic net, and if you go here, it doesn't, if a staff member doesn't manage any properties, like SA9 doesn't manage anyone, you haven't lost any information. That actually shows the true state of affairs. SA9 really is not managing anything. The information that was lost here is that property PA14 is associated with branch 7, but we don't see it. Okay. Okay. So that takes care of that. Make sure I... Okay, the other thing I was going to say is if you have to put this constraint, so it may be that the person insists, no, you really can have unassigned properties, in which case you really do have to explicitly model this relationship, then what you could do is you could, in SQL, put a constraint in the database, a general constraint that says that the staff, the branch, basically it ensures there's equality between the staff and property for rent relations, that it would stipulate that the staff number and branch number in staff must equal the staff number and branch number and property for rent. So you could at least put a general constraint that ensures that they're equal. So if someone updates one but not the other, it would reject the update. You would have to do a transaction where you updated both tuples simultaneously. So that's the other way you could handle it. Okay? Okay. So, moving on. If you have your laptops, I suggest that you now go to my home page, lecture notes, and you'll see something called investment firm design case. It will help for you to have that up on your laptop while we discuss the case. So basically, we're assuming we have an investment firm, and that investment firm manages some clients. The clients own stock. The firm has some offices that the advisors belong to, and we need to model this information in an entity relationship diagram. So there's a number of steps that we described to creating an entity relationship diagram. We first identify the entities, then we identify the attributes, and finally we identify relationships. Okay. Or you could also identify relationships and then attributes. Either way, doesn't matter. Okay, so to start out with, can someone tell me, give me one entity from this case study? Firm. So unfortunately, that is not one of them. Okay, this is good though, because this is a common mistake that is made by, I see in a lot of entity relationship diagrams. So firm is not an entity. It is the database that we're creating the information for. There would, in some sense, be exactly one tuple for firm, right? It's just the firm's name and the like. So firm is not an entity. We're creating the relation for the firm. That's great though, because that happens a lot where I see that mistake made. So firm is not an entity here. Investment advisor. Okay. Client. I think I heard another one. Office. I heard another one. Stock. Okay, dividends is an attribute. Dividends could be stored with stock. Okay, so we don't actually need to have anything else. Pardon? So client is an investor. So I'll just write, that's fine. I'll write, so I'm just going to write in parentheses investor. These are the four. Okay? Advisor, investors, office, and stock. Okay, I like to go immediately to the relationships. Okay, I find it easier sometimes for me to get my attributes once I have the relationship. So I'm going to go directly to drawing the entity relationship diagram. So we have going to write office and advisor, stock, and investor. Now, the way I like to go through on these problems, this isn't obviously the way you could quite do it in the real world, but certainly the problem has a bulleted list of information. So when you're doing it, and this is the way I'm typically going to present the problems, is as a bulleted list of information. In the real world, it'd be a little more amorphous. It wouldn't be spelled out quite this directly for you. You'd have to deduce it. But I think the easiest thing to do to identify relationships is to start to go through each point and see whether that indicates a relationship or not. Okay? So A, the firm has a number of offices. Well, that sentence really just says offices is an entity. Then it says each office has a number of investment advisors who service clients. So that certainly suggests that there's going to be a relationship between an advisor and an investor. Okay, it doesn't tell us about the multiplicity of that relationship. It doesn't tell us anything about the participation rates yet. We hope to get that information later. If we don't, we'll have to circle back, or you'll have to send me email saying, I need more information. The next sentence says, clients own stocks that pay dividends. So it certainly seems there must be some relationship between a stock and a investor. Now, the thing that stocks pay dividends, it's going to turn out that really dividend is simply an attribute of a stock. So we find out an office is managed by one of its advisors in B. Does that suggest we have any kind of relationship? Yes, so we have a manages relationship. Okay, and this actually kind of gives us a good idea of what the participation rates here are. Okay, it says an office is managed by one of its advisors. Okay, so it's not one to many, it's one to one. So an advisor can manage 0 or 1. Okay, so that's, you put it next to how many it can manage. An advisor can manage either 0 offices or 1 office. An office may be managed by a minimum of 1 and a maximum of 1 advisor. Yes, Kyle. We don't. So you're saying, wait. This is manages. So what that is saying is that an advisor can either manage 0. Not every person manages an office. So that's what that is saying. It's saying an advisor can manage 0 to 1 offices. So basically, when you're trying to come up with this one right here, again, think of it as a advisor manages how many offices. Okay, so it can be as few as 0 and as many as 1. The same thing. Now, when we're trying to figure out the opposite, we would say an office is managed by how many advisors. Okay, and it's minimally 1 and exactly 1. Okay, I'll admit I get this messed up all the time, so I'm always trying to come up with mnemonics that help me get the numbers on the right side. Okay, we are going to have a reverse relationship, Kyle, in which you'll see later that an office has advisors, and then there will be another relationship. Yes. You're right. Actually, right there, that one suggests it. So, as pointed out, is that in the second sentence of A, each office has a number of investment advisors. That actually did suggest that there is a relationship of, we'll say, office. I'm going to say, what I use, I'll say has. So moving on to C, it says an investor has a name, a unique investor number, a single investment advisor, and owns 0 or more stock. Okay, so there's some important information in C that we can harvest. Okay, it says an investor has a single investment advisor. So here's this relationship right here, and we have an advisor advises investor. Okay, and we just said in C that an investor has a single investment advisor. So an investor is advised by one and exactly one advisor. Now at this point, I know that I'm pushing the arrow toward investor. You might not have a good idea yet of why the arrow should go that way, but you'll see in a moment why. Okay, so it might be in constructing the diagram that you're, as of yet, not really sure which way the arrow goes. Okay, although the fact is in A, it said advisors who service clients. That's kind of already implying that it should be in the direction I show you there, that an advisor is probably going to advise multiple investors. So A has a hint of which way the arrow goes. Okay, C contains another important piece of information. What's the other important piece of information for relationships for the ER diagram? 0 to many stocks. Okay, so an investor owns 0 to many stocks. Okay, so that takes care of C. The rest of the information in C gives you attributes for an investor. Okay, so we'll move on to D. It says each investor's holding of a stock, so that contains information about the stock's ticker symbol, the stock's name, the number of shares of stock owned by the investor, and the dividend per share paid by the stock. And we only keep track of the investor's cumulative holding. We do not care about the individual transactions that led to this holding. Okay, now, okay, so the stock, this really only, did this give us any additional information for relationships? Okay, so we can go through it. Stock's ticker symbol, that sounds just like an attribute, right? Stock's name, sounds like an attribute. Number of shares of stock owned by the investor, sounds like an attribute. Dividend per share paid by the stock. None of those is indicating a relationship with anything else. Okay, it's just basically giving us information about the attributes of a stock. So there's nothing in D that allows us to add information to this ER diagram. The dividend is a dividend per share, so it's the dividend that is paid. No, a dividend is paid to the person who owns the stock. So stocks can pay dividends. Like if I own 100 shares of IBM and IBM pays a 10-cent a share dividend, then IBM periodically is going to send me a check for $10. The investor gets it directly, typically.
So is there a relationship between stock and investor?
There is, which is investor-owned stock.
But
Okay. There may be another relationship that we have to somehow determine what this other direction is. Okay. But it's not clear that D gives us that information. Yes.
Correct me if I'm wrong, but given what's listed on D, we don't care about the price per share. We only care about what the investor has from that
That's correct.
stock right now.
Mm-hmm. Probably you would, no, that's a derived attribute. Okay, because the price per share ultimately is you're going to see when we get down to J. So it's hard, I mean, you kind of have to read everything, I guess, too, and know what's coming. So J is going to say there's some purchase records, okay? So presumably the average price per share is going to come off of those purchase records as a derived attribute. Okay, other questions? Okay, E. An investment advisor has a name, a unique advisor number, one or more clients that the advisor services, and in an office to which the advisor belongs. Okay, we got some important information there. Okay, the reason in general, anytime something refers to another entity, we've got important information. So an investment advisor has a name. Okay, that's an attribute. That's not referring to anything else. A unique advisor number, again, that's an attribute, presumably a primary key, right? Unique. Okay, so at least your antenna should go up that this is probably a primary key. The next one, though, is interesting. One or more clients. A client is an entity. Okay, that's an investor. I understand. I should have been consistent in my wording, but it's an investor. One or more investors that the advisor services. Okay, so we have right here, this becomes, well, advises. You also have to know where we're going, but an advisor advises one to many clients because it says one or more clients that the advisor services. But it goes on, and an office to which the advisor belongs. That again should be ding, 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 office. Okay? What is the relationship? What can we fill in? Right, it's this relationship here, but can I fill in this side of it or this side? 1 or 2? 1. Very good. And it's 1 dot dot 1. So it belongs to exactly one office. Okay, so we're making good progress. In fact, we're only missing right now this one and this one thus far. Okay. So F, an office has a office number and an address. Anything? Pardon? Yep, both of those are office attributes. So those are attributes we'd add to an office. Okay. G, that kind of, an advisor is associated with only one office. It is information, but it kind of repeats E, right? In E, I said an office to which the advisor belongs. In G, I said an advisor is associated with only one office. So you could kind of think of G as saying, as really specifically saying only one office. But E kind of already had said it. So I'd already inferred it from E.
E doesn't say that the advisor can't have more than one office.
It doesn't really say it, you're right. It kind of implies it, though, when it says an office. It doesn't say offices. So I kind of feel like G is a bit of repetition, but it certainly makes it concrete, right? You certainly know now it's just one. Okay, an office H. An office may have multiple advisors. Okay, so which one? Is it this one or is it that one? This one. Okay, and what is it? One many. So we can have, an office may have multiple advisors. Now it doesn't really say whether it's 0 to many or 1 to many, but I'm going to assume 1 to many. That's certainly something you'd need to verify with whoever it was you're constructing the database for.
It's 1 because A says each office has an advisor.
Ah, you're right. Each office has a number of investment advisors. Certainly implies 1 to many. Okay, but it's possible if we're building one, we're putting it into the database and it might not yet have any. But at any rate, we'll say 1 to many. Okay, I, the dividend per share is determined by the stock. The dividend per share is determined by the stock. This is a toughie, okay? This is a bit of a curveball. This is something that you would probably only be able to resolve when you get to bottom-up design. Remember I said entity relationship models are top-down and that normalization is bottom-up? It turns out that I is something that is easily handled when you think about design from a normalization standpoint and not easily handled when you're thinking about a entity relationship diagram. Now, I can tell you what it means, which is that you really have, remember, you have a so-called weak entity relationship here. So if I go back, I'm not finding it. Certainly wasn't there. There we go. It was this slide. This is what we actually have with I. We have a strong entity stock, which has a attribute dividend that we really don't want to store in every tuple because it will create duplication, right? Because if you think about it, a stock is it's possible for a stock to be owned by multiple clients, like IBM. And if we have multiple tuples for IBM, we probably don't want to store the dividend in every single instance of a tuple, right? Because there's a good chance when IBM changes the dividend, we may not actually update every single tuple. So ideally, we would create a so-called weak entity called dividend. And it's going to be stock. Okay. And over here, it's going to be dividend. And again, a lot of you will want to say has. How about pays? Stock pays dividend. So I is actually setting up, turns out, a weak entity called dividend. Okay, now dividend is an attribute. So what it's really going to be is, but you might call it, for example, the relation might be dividend paying stocks, might be the name. Not all stocks pay a dividend. So you might call the relation dividend paying stocks, and you'd have a stock ticker symbol probably, and the dividend amount. So this is a classic example of a weak entity. And again, it's a lot easier to see that one when we get to normalization. It's a lot harder at this point to handle it with top down. This is the kind of relationship that is not well handled by the top down approach. It's handled much better by the bottom up, which is why you often do both. Okay, so you do have another one right here, which is, I'm going to call it dividend paying stocks. And pays. Okay. So the multiplicity, a stock does not have to pay a dividend. But if it does, it will be there only once. So a stock may or may not pay a dividend. Not all stocks pay dividend. A lot of tech companies don't pay dividends. They want to reinvest everything. But a dividend is always associated with a stock. Well, that's a bug. I'm sure I didn't do that. Okay, so it's one, a dividend is a one, minimum of one, and maximum of one stock that it's associated with. That's the classic weak entity relationship, which is in a classic weak entity relationship, the weak entity, the controlling entity, which is stock, will have 0 to many instances of it or 0 to 1. And in the opposite direction, the weak entity will be associated with exactly one strong entity occurrence. That's the classic relationship multiplicities or participation rates. Okay, so this weak entity is always associated with exactly one instance of a strong entity. The strong entity can have 0 to either 1 or many instances of the weak entity depending on what it is we're talking about. Okay, telephone numbers, branch to telephone numbers. It turns out a branch can have 1 to 3 telephone numbers. So in effect, telephone number has to be represented as a weak entity. So multi-valued attribute is modeled as a weak entity. It has 1 to 3 occurrences, but each phone number is associated with exactly one branch. So questions about that? As I said, this one's a tough one.
Always multivalent attribute, the weak entity.
Pardon, what?
Is always multi-valued.
Not always. You could have potentially, I think this example showed,
For example, some staff.
this one here, this one actually had a preference and a maximum rent. So here it was actually 2 attributes. So it's not guaranteed to be only 1. Okay, in my experience, it's typically only 1, but it's not necessary. Okay, but typically you're right. It's typically off of a multi-valued attribute. Other questions? Okay, the last one's tough too. Okay, so when a stock gets purchased or sold by an investor, we record the stock ticker symbol, the transaction price, the date, the number of shares purchased or sold, the investor who purchased or sold the stock, and the broker who conducted the transaction for the investor. Okay, so a stock, so that's an entity, gets purchased or sold by an investor. Okay, that sounds like a relationship between a stock and an investor. Okay, we record the stock's ticker symbol. That sounds like an attribute. The transaction price, that sounds like an attribute. The date, that's an attribute. The number of shares purchased or sold. The investor who purchased or sold the stock, that's an attribute, entity, but we already knew that. And the broker who conducted the transaction for the investor. Okay? We don't have anything here showing that. A stock gets purchased by an investor, and we also include the broker who conducted the transaction. This is a ternary relationship. There's 3 entities involved in this. A broker transacts the purchase of a stock for an investor. It's a ternary relationship. So what we have, well, that was nice, Brad. Okay. Purchases. Okay, so we have a stock, an investor. Broker is an advisor. Okay, I can see now, I do a lot of investing, and so I'm conversant with the different terms. I could see where this could be confusing, so I have to be careful about the wording. But a broker in this case is the same as an advisor. Okay, so that's a 3-way relationship. You can tell it's a 3-way relationship because it mentioned 3 entities in the same sentence. So don't represent it as 2 binary relationships. It really is a degree 3 relationship. Okay? Yes.
If an investor sells all his stock, and there will be another new investor that can.
Well, but it depends. Yes or no. I mean, someone at another company might buy the stock. It doesn't have to be bought. It doesn't have to be sold to another one of our investors. It might be sold, like if I'm Merrill Lynch, okay, maybe I sell the stock, but it might be sold to someone at Scottrade or Ameritrade or one of the other brokerage houses. So there's no guarantee that.
We don't need sales relationship.
Well, I'm sorry. I see what you're saying. Let's change it from purchases to transacts. Okay? That way it can be either a purchase or a sale. Okay, and now we have to set up the 3 participation rates. Okay, so let's start with a investor and an advisor. So if I have a particular advisor, let's say advisor 301 and investor I32, how many stocks do you think the advisor may have brokered for the investor? 0 to many. They may have sold 0 thus far. They may have sold many. So that one's 0 to many. Okay. If I have a stock and an investor, okay, so if I have some stock like IBM and an investor, now think about this one for a moment. Okay, what's the obvious answer? If you have a investor with a stock, someone had to have sold it to them. It can't be 0. Okay, you had to do the transaction with someone. So if the investor has a stock, there has to be someone who sold it to them. The minimum has to be 1. Okay, minimally it has to be 1. The question is, did the advisor piss off the investor so that the investor moved to another advisor or not? Okay, you've had it happen, right? Maybe not with an investment advisor, but maybe an advisor here at UT, you just didn't work well with the person, so you moved to another one. So probably the answer is, it depends, but there's a good chance it's 1 to many here. Not going to say it's not 1 to 1. I would take it as 1 to 1. I'm just saying that's one you have to think about. And then we have the last one, which is going to be if we have a certain stock in an advisor, so an advisor and IBM, how many times could an advisor have placed that stock? Could the advisor have multiple investors with that stock? I see Kyle nodding his head. Yes. Certainly possible that you'd have several investors with IBM stock. And it could be no one. You might not sell the stock to anyone. So for a particular investor, or for a particular stock and a particular advisor, it might be 0 to many. Okay? So that gives you the entity relationship diagram. I'm going to publish the solution. I'm going to let you look over the attributes and the foreign keys. I think it's pretty obvious based on what we've done what are the attributes and the foreign keys. Also remember on Thursday we do not have class, but you do have a video lecture to look at. And on Tuesday we're going to go directly into a case study for normalization. So listen to the video lecture because it's going to talk about normalization. So even though there's no class on Thursday, make sure you watch that video lecture by next Tuesday. And also, even though there's no class on Thursday, you have a homework assignment due Thursday.